Hello everybody and welcome back to the channel. This is Dave. In this video, we're going to be continuing in our series about algebra topics. And in particular, we're going to be talking about multiplying polynomials. Before we actually get into multiplying algebraic polynomials, let's look at an example from arithmetic so that we can understand the process. Let's suppose that we wish to multiply the quantity 5 plus 3 plus 6 by the quantity 4 plus 2. Obviously, we can add the numbers up to get 14 times 6 equals 84 by observing the order of operations and first simplifying what's inside the parentheses. However, we can also represent this geometrically as a rectangle. This rectangle will have a width that is 14 and is broken up into segments of 5, 3, and 6. It will also have a height of 6, which is broken up into segments of 4 and 2. In this case, the total area of the large rectangle is nothing more than the sum of each of the 6 smaller rectangles. In other words, we can express the sum of the quantity 5 plus 3 plus 6 times 4 plus 2 as 5 times 4 plus 5 times 2 plus 3 times 4 plus 3 times 2 plus 6 times 4 plus 6 times 2, or 84. In any case, it's identical to multiplying 14 by 6. So what did we do in order to expand this expression? Well, we multiplied the first number in the first factor by the first number in the second factor, 5 times 4, and then we multiplied 5 times 2. So we multiplied the first number in the first factor by the second number in the second factor. Then we moved on to the second number in the first factor and multiplied it by the first number in the second factor. And then we multiplied the second number in the first factor by the second number in the second factor. And we continued to do this until we reached the end of the line. Thusly, so to get the product, we multiplied every term in the first factor by every term in the second factor. We will apply the exact same logic to multiply algebraic terms. So here is our first algebraic example. We want to expand the product of the quantity x plus 2y plus z times x plus y. And to do this, we must recall a property of exponents, namely that when we multiply two quantities with the same base, we add the exponents. So multiplying x to the m power by x to the n power results in x to the m plus n power. We'll first do this graphically so that we can see it and understand it. We start by multiplying x by x and get x squared. Next, we're going to multiply x by y to get xy. We'll then move on to the second term of the first factor and multiply 2y by x to get 2xy. Then we'll multiply 2y by y to get y squared. After that, we will move on to the third term of the first product and multiply z by x to get xz. And finally, we will multiply y by z to get yz. Again, the sum of all 6 of the small rectangles is equivalent to the sum of the large rectangle. So all we have to do is to sum up each of these smaller rectangles. So this gives us x squared plus xy plus 2xy plus 2y squared plus xz plus yz. The last step, of course, is to combine like terms. So our final answer is x squared plus 3xy plus 2y squared plus xz plus yz. Let's look at another example. We want to expand x plus 2 times x minus 3 times x plus 1. We're going to multiply x plus 2 times x minus 3. Then we'll multiply the result by x plus 1. To do this, we'll use the FOIL method. And this gives us x squared minus 3x plus 2x minus 6. Or, combining like terms, x squared minus x minus 6. We will then multiply this by x plus 1. So to do this, we multiply x squared by x, giving us x cubed. Then we multiply x squared by 1, giving us a positive x squared. Next, we'll multiply negative x by positive x, giving us a negative x squared, and negative x by positive 1, giving us a negative x. Now we come to the last term in the first factor, which is negative 6. So we multiply negative 6 by x to get negative 6x, and negative 6 by positive 1, which gives us negative 6. After this is all done, we can now combine like terms, and we get x cubed minus 7x minus 6 as our final answer. In this case, it just so happens that the x squared terms cancel out, but be aware that usually there will be a quadratic term in your answer. Moving on, there's a special case of a plus b to the nth power. And this can be very easily found using a very powerful tool known as Pascal's Triangle. What is Pascal's Triangle? Well, it's a famous number pattern that has many interesting properties, as we'll see later on. The triangle may be constructed in the following manner. In row 0, which is the topmost row, we have a single non-zero entry, 1. In the next row, row 1, the entries are 1 and 1. And each entry of each subsequent row is constructed by adding the number above and to the left with the number above and to the right. So in this example, to get the third row, we would add 1 plus 1 and get 2. Then in the third row, we would add 1 plus 2 to get 3, and again add 2 plus 1 to get 3, and so on. Let's take a look at the first few instances of the expansion of a plus b to the n and see how they're related to Pascal's triangle. So a plus b to the 0 power is 1 because any quantity to the 0 power is always going to be 1. A plus b to the first power is equal to 1a plus 1b. We're intentionally inserting the coefficients here so that we can recognize the pattern. And of course, this is true because any number to the first power is itself. Next, a plus b is equal to 1a squared plus 2ab plus 1b squared. And a plus b to the third is equal to 1a to the third power plus 3a squared b plus 3ab squared plus 1b cubed. Based on this, what kind of patterns can we see in this, and how is it related to Pascal's triangle? Well, the powers of a start at n and decrease until 0. The powers of b start at 0 and increase until n. The sum of the powers of a and b is always equal to n, and the coefficients of each term corresponds to the numbers of the nth row of Pascal's triangle. Keep in mind that the first row, where we simply have the number 1, is row 0. So we can see very clearly how Pascal's triangle could help us to find the expansion of a plus b to the nth power. Let's continue exploring the expansion with a plus b to the fourth power, which is going to be equal to a plus b cubed times a plus b. We will see that this also corresponds to the fourth row of Pascal's triangle. If we do this and we multiply each term in the first factor by each term in the second factor, we get a to the fourth plus a cubed b plus 3a cubed b plus 3a squared b squared plus 3a squared b squared plus 3ab cubed plus ab cubed plus b to the fourth. When we combine like terms, we get 1a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the fourth. Indeed, we can see that this conforms to the fourth row of Pascal's triangle. As our final example, we are going to expand the quantity x minus 2 to the fourth using the shortcut of Pascal's triangle. It's always a good idea to try and identify a and b. In this case, a is simply x and b is negative 2. We'll recall the rules for expanding by Pascal's triangle. Namely, the exponent of a starts at n and decreases by 1 until you get to 0. The exponent associated with b starts at 0 and increases by 1 on each term until you reach n. And the coefficients are equal to the numbers in that nth row of Pascal's triangle. So if we do this and we follow the pattern, we get x minus 2 to the fourth power is 1 times x to the fourth times negative 2 to the 0 power plus 4 times x cubed times negative 2 to the first power plus 6 times x squared times negative 2 to the second power plus 4 times x to the first power times negative 2 to the third power plus 1 times x to the 0 power times negative 2 to the fourth power. At this point, all we have to do is we have to simplify this. So when we simplify it, we will find that x minus 2 to the fourth power is equal to x to the fourth minus 8x cubed plus 24x squared minus 32x plus 16. One very quick thing to note here is that the signs of the terms alternate between positive and negative in this particular example. That's because b is equal to negative 2, and anytime we raise a negative number to an odd power, we naturally get a negative number. And anytime we raise a negative number to an even number, we get a positive number. So this is what causes the terms to alternate. So I hope you enjoyed this video, and I hope it was helpful in your studies. If you liked the video, please subscribe and give a thumbs up. Thank you very much, and I hope to talk to you again in the next video.